There's one concept I would like to review from Part 6, because there are many subtleties here which are particularly pertinent when I start talking about materials and electronic properties. And if you refer to the lower diagram, and as you might recall, I've graphed out the energy levels of a hydrogen atom. So we're looking at it from the side in a stretched fabric representation with a proton in the middle. So this is a side view plotted along the vertical axis as energy. And if we were to look at it from the top, we would see a spatial plot of the orbits. Normally in hydrogen, the single electron would be at the ground state, and in order to get that electron out of the atom, you would have to supply the ionization energy to that electron. Otherwise, it would stay down near the proton in a tight n=1 orbit. Now that energy can reach the hydrogen atom in a number of different ways. One way would be to hit it with a photon of light that carries the appropriate amount of energy. Another way to get that electron out of the atom would be to apply a very large electric field nearby so that the electron would gain enough energy in its orbit to be sucked out of the atom by the field. It's not possible for the electron to exist for any more than a very tiny amount of time between these various levels. So you could say that these levels plotted out by the green lines are quasi-stable in that sense. So if an electron can exist here for a time at the n=2 level, and if the electron were orbiting at the n=2 level, then it could lose energy, for example, by emitting light in order to return to the ground state, the n=1 level. Now that's completely different from the planetary picture with the gravitational force. We've got the Earth here at one energy level, in one orbit, and we have Venus closer to the Sun in a tighter orbit. Now that doesn't mean that orbits cannot exist between these two, and in fact there are small rocks and asteroids all orbiting all over the place in the solar system. So don't confuse these two pictures here. But quantum mechanics will prevent any electrons from orbiting the hydrogen atom in between any of these two permitted levels here. In other atoms, these levels might all exist at different energies, and it should make sense that the levels wouldn't be the same as in hydrogen, because in anything other than hydrogen, we would have more protons in the center, which in the stretched fabric representation here would weigh down the fabric more with the increased positive charge and change the curvature of the space. Furthermore, if we have more than one proton, like in helium, then more than one electron would normally be in orbit at the same time. The electrons are, of course, attracted to the protons in the nucleus, but electrons simultaneously repel one another. So in atoms other than hydrogen, this interaction causes the permitted energy levels to have a complicated relationship with the number of electrons present. Allowed energy levels are also unique for molecules. For example, if I have one hydrogen atom with the allowed energy levels shown in the view graph, it's not difficult to imagine that if I take another hydrogen atom and I move it nearby, then all of the energy levels might be disturbed. In Part 4, we've seen an animation of what would happen to the solar system if we brought another star nearby. We saw that the orbit of the Earth could be disturbed. Similar, the orbit of an electron in a hydrogen atom would certainly be affected if another hydrogen atom were brought close by. When an electron is moving through a dense material, it sees a complicated landscape around it consisting of atomic nuclei and other electrons. In a solid, the atomic nuclei are all locked in place very close together, so electrons see a very different environment than they do in a gas, where atoms are a lot further apart. You've probably all seen power lines at one point or another. If they're high off the ground, there's no need to insulate them. They're just bare aluminum. Aluminum's cheaper than copper and less likely to get stolen. In fact, there have been cases where thieves have tried to steal copper power lines before. Sometimes they were successful and sometimes they died. People assume that when you get near one of these electrical wires, it's safe as long as you don't touch it. And of course, that's not true, because air breaks down if there's a high voltage nearby. If you ever see, for example, a downed power line, you cannot assume that it's safe to be even near it. And here's the reason. Air breaks down at an electric field strength of about 3 kilovolts per millimeter. That means that if you're grounded and you're near a power line carrying, say, 3,000 volts, then you can get within about a millimeter of it before there'd be a spark. But any closer than that, then the air would break down because of the strong electric field created by the high voltage in the line and the ground, 0 volts from your body. A spark would leap off of the power line into the part of your body closest to it through the air. A spark is a conductive plasma of air which connects the body to the power line, and that would be very bad news. Some of these high voltage lines, especially the ones that are way off the ground, they run several hundred kilovolts. So from the breakdown voltage of air, which is only an estimate since it depends on humidity, pressure, and temperature, you should in theory be able to calculate how far away you would need to be from an electrical line to avoid getting a shock. A downed power line isn't safe at all, even if you're nearby. It's interesting that power lines are often serviced while they're still live. Let's look at an interesting video now of power line workers approaching a live power line by helicopter. Obviously, a power company doesn't want to shut down a high voltage line unless they really have to, because these lines carry a lot of power to customers. So this is an example of a line worker on a helicopter getting ready to fly towards a high voltage power line. And what I want you to notice is that there's obviously no danger until the helicopter gets close to it. Now, this one is also interesting. As he approaches the high voltage line, the man has a pole that's used to charge the helicopter to the voltage of the line. When the lineman reaches a certain distance from the line, current will start flowing, and the current will stop flowing through the sparks once the helicopter is at the same potential as the line. And now it's safe for him to remain on the line and attach himself to the line. So if the power line were instead near the ground, you certainly wouldn't want to get very close to the line, and I would leave a good margin of safety. So we've seen situations where air can break down and create a spark, in which air can become conductive and current can flow from one electrode to another, for example. This happens when electrons are stripped away from their orbits. But what happens when the material is not air? In the next video, I'm going to introduce a machine which can create high voltage differences across 2 electrodes, called a Wimshurst generator. We'll first see how well the machine works in ordinary air, and then in a subsequent video, we'll operate the machine in other gas atmospheres. So in front of me now is a Wimshurst generator. It's a machine that was designed during the 19th century in order to separate charges. As I turn the crank back here, these wheels are going to spin, and what happens is it causes one of these electrodes to become more and more negatively charged relative to the other electrode. Of course, anytime you have a charge difference from one place to another, you have a voltage difference. Electric field strength equals voltage divided by distance. So as the voltage grows and grows as I spin the crank, the electric field strength between the 2 electrodes also increases. And eventually that electric field strength will get so high that the air will break down and we'll get a spark. When we get a spark, of course, then the electrons will stream across the conductive channel created by the spark, and then everything will be neutralized and the process will repeat. The voltage will start again at 0 and then grow and grow and grow until we reach the necessary electric field strength in order to break down the air. But what's interesting is that if we start with the electrodes close together and I try to maintain my cranking at a relatively constant rate, then what will happen is as I move the electrodes farther and farther apart, then the sparks will occur less frequently. And of course the reason for that, again, is that electric field equals voltage divided by distance. And as the distance between the electrodes grows, the voltage necessary in order to reach that electric field to break down the air is going to increase proportionally. So let's give it a try here. I'm going to start with the electrodes fairly close together. And as I spin the device around, we start getting sparks between them. And I'm now going to separate the electrodes a little bit. we're getting fewer and fewer sparks because it takes longer between each spark to reach the necessary voltage to break down the air. In the next video, you'll see that we've modified the Wimshurst generator so that we can fill the area between the two electrodes with any gas that we want. We've installed an acrylic box now over the electrodes, and the box has a small hole where we can temporarily attach a gas cylinder. It's not completely airtight, and in fact we have a small exhaust hole drilled into the box so that the new gas that we introduce can push out the air that's ordinarily in there. We're in Singapore now during this experiment, and the humidity is always a big problem here, so this also helps to push the humidity out of the box. So with this experiment, it's important to use inert gases in a well-ventilated area. So the first gas we're going to try is helium. Now what I want you to do is notice that with the helium, no matter what we do to the electrodes, you can't really get a good spark at all, hardly anything. If you look at it really closely though, you can see a kind of a little purple discharge right in between the two electrodes. But the point here that I'd like to make, firstly, is that helium behaves differently than normal air. Now we'll try pure nitrogen. And you see, even as we pull the electrodes apart, we can get quite a good spark between the electrodes. So let's lastly try argon. So we've got a cylinder of argon in the lab that we use for certain semiconductor fabrication processes. So we've temporarily repurposed the cylinder for a few minutes to do the demonstration, and I think argon is the most interesting gas. Now we start the experiment with the cylinder turned off, and nothing really happens because when the electrodes are far apart. And as we open the argon cylinder, it's clear that many small sparks are flying between the electrodes, and the colors are different than in the case of nitrogen. Now, this demonstration was, of course, carried out at atmospheric pressure. We didn't try to reduce the pressure somehow because we didn't have an airtight container. But if it had taken place instead at a lower pressure, the sparks would have been much more intense because the atoms would have had more space between them for electrons to accelerate to higher velocities. So in fact, less voltage would normally be needed to ionize a gas if the pressure is reduced. And this is something that's been measured before. This graph illustrates what's called Paschen's law, and we can now say something more about the experiment with the Wimshurst generator that we've just seen. Here is graphed the breakdown voltage versus the pressure times the distance between the electrodes. So if you look at the horizontal axis, lower pressure is on the left, higher pressure is on the right. Shorter distances are on the left, longer distances are on the right. And if you're intentionally trying to create a spark, you would want a low voltage, meaning it would be easier to ionize the gas. And if you look at this curve, argon has the curve that dips down the lowest. And we saw in the experiment with the Wimshurst generator that argon did create sparks fairly easily. Nitrogen and helium are also both shown on this graph. Now let's look at the right part of the graph, and all of the curves are nearly straight lines. This happens naturally because electric field strength is just voltage divided by the distance. So as the voltage increases, the distance increases at the same rate to create the necessary electric field, which would break down the gas. Now on the left part of the graph, the electrodes are getting rather close together. and then the curves all start to rise again. This happens because when the electrodes are so close together, electrons, which have been stripped from their host atoms through ionization, don't have enough space to accelerate. They don't have enough room to build up enough speed to trigger the type of avalanche that would ionize many other atoms. So it's naturally this case that these curves would all be a little bit different because these gases all have different molecular weights and hence different densities at a given pressure, and they all have different electron configurations. With helium, for instance, its 2 electrons completely fill its s orbital and are very tightly bound. This would ordinarily mean that it's hard to ionize a helium atom. And indeed, it's really hard to ionize a helium atom by applying a static electric field. But helium is also the lightest gas, so it has a lower density than the other gases on the chart. And when an electron is freed, then it can reach a higher velocity before a collision than a free electron would be able to in another gas. So you can say that a single helium ion is hard to ionize, but it's easier to ionize it when you have a lot of it. This is evident in the plot. It's clear that at short distances, helium is difficult to ionize because the breakdown voltage is just so high. But at long distances, the avalanche condition is easier to reach, and helium becomes easy to break down, and its breakdown voltage is lower than that of the other gases. In this video, we've seen what happens when you apply a static electric field to a gas at atmospheric pressure. We've seen that different gases break down at different voltages. In the next video, we'll experiment with gases at very low pressures, and we'll look at what happens when the polarity of the voltage is changed very rapidly.